Alright guys, welcome to another short video here. Today we're going to look at direct stress, strain and elastic modulus. Now this is sort of a recap or an introduction of some stuff we've done in class. Now to try and get your head around this question, I've put some images together for you. Okay, it's got a house with a balcony and it's got these two things at either end of the balcony, and these are classed as struts, which is where this word comes up here. So a strut allows a load to be applied to it in a compressive direction, so that's being squashed in there. Okay, the strut itself is got a diameter of 80 millimeters and it's also got an inside diameter, so that tells us it's a circular shape with a big hole in it. It's got a length of 3 meters. Okay, here's our units for that, and then we've got a force here of 10 kilonewtons. Okay, we've also got ultimate compressive stress of 350 megapascals in elastic modulus of 180 gigapascals. Okay, now we don't actually need the compressive stress, so you can forget about that for now. We might need that on some future questions, but for this one we don't. Okay, so first things first, what's that asking us to do? It's asking us to calculate the compressive stress in the material. So what stress is in this material here, and it's also asking us to work out what change in length takes place after we put this load onto it. Alright, now as I said, to help you do this, obviously you've got your formula sheets, you've got your direct stress calculations. Stress is force over area. You can see strain and elastic modulus formulas there too. But just so you can sort of visualize what's going on here, we've got these little free body diagrams. Ground, strut coming down vertically, which is supporting the load, and we've got our force coming down on top. Okay, so this might help you sort of get your head around what's going on in this question. Next thing we'll do is we'll have a little look at the shape of the strut itself. It's got an outside diameter of 80 and it's got an inside diameter of 74. Now that is going to allow us to calculate the radius of this object, because we're going to need that for our area calculation. Pi big R squared minus pi small r squared. Alright, now don't forget these values are going to need to be turned into meters when we do our area calculation. So we'll jump onto the next slide and we'll actually have a little look at the units that you'll end up with when you're using these. So the three formulas we're going to need is this one, and this one. Now we're not going to need that one, but that might be something we'll come across in future videos. But again, if you're trying to sort of struggling to get your head around the units, just pause the video and you can start to jot all them down. As and when you need them, you can go back and refer to them. So again, let's skip ahead and we'll have a look at how to solve this problem. So first things first, we're going to calculate the area of this object. So area equals pi times big R squared minus pi small r squared. There's something that you're going to have to be aware of for future questions is the object isn't always round, so you might need your base times height calculation for your any rectangular or square objects that you're working the stress out on. So we're going to go ahead and we're going to do area equal pi. So we've got our big R, which is our 80 millimeters. That's the diameter. We need to divide that by 2 and then divide it by 1000 to turn it into meters. So we're going to have 0.04 squared minus pi times small diameter divided by 2 and then divided by 1000, so 0.037 squared. Now don't forget, both parts of this need dividing by 1000 before you work them out. You'll get a completely different answer if you do the calculation and then divide by 1000, so just bear that in mind. So I'll give you a sec just to get on your calculator and you can get an answer. So we should get 726 times 10 to the minus 6 meters squared for our area. Now the more experience you get with these, you'll be able to put that formula straight into your stress equals force over area question. So let's go ahead and work out what stress is here. Area is stress is force over area. So force is 10 times 10 to the 3. We've got our area 726 times 10 to the minus 6. And again, pause the video, pop it in your calculator, let's see what answer you get. We should get 13.8 times 10 to the 6 pascals. Alright, now if you're not getting that answer, just go back and recheck how you popped that into your calculator, but I'm pretty confident that that's the right answer for the stress part. Next thing we're going to do is we're going to start to look at the change in length of the strut. So we apply a load to this object, it's going to get squashed. How much is it going to get squashed by? That's what we're working towards solving here. Now to do that, we're going to need both of these formulas. We're going to need strain and modulus of elasticity. Now if you think of the previous information we had up, the change in length is represented by the delta L, so change in length. So we're going to need this formula, but not in the format that it's in. We're going to need to rearrange that. So stress is equal change in length divided by original length. So to work out the strain, which is what we're aiming for, we're going to need to have a little think about our next part to this equation. Right, but let's go ahead and we'll rearrange the change in length formula. So it's going to be equal to strain times original length. Now we know our original length, we've got that up here, it's 3 meters. Alright, so I'll lay that out times 3, and that's going to give us our change in length. But I don't know what this strain is yet, so I'm going to have to jump onto my next formula here. So I've got elastic modulus is stress over strain, so strain is going to equal stress over elastic modulus. So stress we've got from earlier, 13.8 times 10 to the 6. Divide that by our elastic modulus, which is 180 times 10 to the 9. Alright, so we've got giga 9. Now if you're struggling to remember the difference between these, go back to your previous notes or the previous videos and see if you can just re-familiarise yourself with them. Now, on the top we've got pascals and the bottom we've got pascals, and so there isn't actually any units for strain, so that's one of the only areas in engineering where there isn't any units, so just bear that in mind if you gain some answers. So the answer to that, and I'll let you pause your video and then you can pop that in your calculator. So the answer we get for strain is 76.5 times 10 to the minus 6. Okay, 76.5, and again, no units for that. I'm going to do 76.5 times 10 to the minus 6. Now if you're getting 10 to the minus 4 up here, then your decimal's in a different place, then just press your ENG button and then you'll get to the same answer. So those two are going to get multiplied together, and that's going to tell us what the change in length is. So in that case, we're going to end up with 230 times 10 to the minus 6 meters, because it's a length. The original length goes into meters, so therefore our final answer is going to be meters. So that's a sort of minuscule value, but obviously, you know, the bigger the load we put on this, the more it's going to get squashed, the more the length's going to change because the stress will increase, etc, etc. Okay, so there's a few things going on there. Main thing that I've been noticing with students is that they're struggling to interpret the question. So if it's a square bar or a rectangular shaped bar where the load is being applied to, then you're going to need your old base times height question formula, sorry, and again in meters, or if it's a circular one, it might be area is pi r squared, or if it's a circular one with a hole in it, and again it'll be the one that we've just used, pi big R squared minus small pi r squared. So again, just double check what shape you're dealing with, and that's commonly given to you in these values that are given to you in the question. Alright, so hopefully that's been of use to you. Now there are quite a number of examples of this in your workbook. Around about page 30ish, I can't remember off the top of my head what page it is, but if you have a look at in your workbook itself, there's loads of different examples. So work on your presentation, and if you want to hand them to me at some point, I can check you're getting the right answers, and then we can hopefully move on together with this. Alright, now again, thanks for watching. Go back to the bit that you may be struggling with, pause it, jot it down, make sure you're getting everything written down, and then have a go at the questions in your workbook. Once again, thanks for your time, and hope this is of some use to you and it comes in handy in the future. All the best, thanks, bye.